All right, well, isomers are one of the tougher portions of the homework, and that's because it's kind of trial and error in order to understand them. So the easiest way to get good at anything is to practice, and that's what we're going to do. In small isomer kinds of ideas with smaller carbon chains, you don't have to worry about isomers at all because there's no multiple way, there's no different way in order to draw them. The definition of an isomer is same formula, so same number of carbons and hydrogens, but a different orientation or different structure of how you connect them together. So you can imagine that if you have CH4, which is the simplest hydrocarbon methane, there is no different way to draw it other than just a dot. So you don't have to worry about isomers for methane. Even if you look at ethane, which is C2H6, so double plus 2 would tell us the number of hydrogens, you can only draw a line, and that's the only way that you can draw it. So there is no isomers for ethane either. Even propane, C3H8, would only have 1, 2, 3 carbons, and whether you draw it upside down or right side up, all of those are the same, and there is no isomers for propane either. So that's why natural gas tends to be a little bit cheaper than gasoline, because you don't have to remove all the isomers that exist. They give it less heat or less power. As soon as we go to 4 carbons, we do have a choice though. We can have 4 across. This would be for C4H10. This is typically the butane molecule, so in this case we can see butane as 1, 2, 3, 4. And that butane name is probably the easiest isomer to think about. It's just 4 in a row. But you can imagine that if you have 3 in a row with a branch, that's also 4 carbons. It's also 10 hydrogens. But now, because this is attached to the parent of 3, we would call it a 2-methyl propane. And that's different. So anytime we can draw a structure differently, but it ends up having the same number of carbons and hydrogen atoms, that's what an isomer is. And this is why gasoline can get expensive. Gasoline is octane, which is C8H18. So double plus 2, double is 16, add 2 hydrogens, you get 18. But they have to take away all the other isomers, which there's over 50. And most crude oil samples of gasoline, that has to be purified, has to be distilled away from the others. And the longer they distill, the more octane they can get, but also they're going to return that cost as you get to those higher octanes of 87, 89, 91, 93, up to racing fuels of 104 and 110 and so forth. So it's more expensive to remove, say, this isomer from this one. So butane that you put in lighter is a little bit more expensive because you have to remove the other isomers that are very similar in size, identical in atoms, but different in shape. So let's think about the other isomers real quick. So we already said that methane and ethane do not have isomers because they're too small. Propane fits that category as well. But as soon as we got to C4H10, we had 2 isomers, and that was 4 across or 3 with a branch. If we get to, so it's got 2 isomers total. If we get to a larger formula, say C5H12, we could have 5 across. And then we could also have 4 across with a branch. Just realize that if we do 4 across with a different branch, we would just number it from this side rather than that side. And that one's the same. So that's a repeat. So we don't want that one. But we could go to 3 and then add 2 branches. That's still 4 bonds to carbon. That's still not breaking the octet rule. So that's the difference between, say, pentane up here, 1 isomer. This is a 2-methyl butane, 2nd isomer, and this would be a 2,2-dimethyl propane that we saw previously in a different video. So C5H12 has 3 isomers, not 2 that we saw over here for C4H10. It had only 2. In the homework, they're going to go one step further. They're going to ask you for C6H14. So double plus 2, double is 12, plus 2 is 14. This is the most saturated form of 6 carbons. So this would be hex, that's 6 in a row. 1, 2, 3, 4, 5, 6. We could do 5 in a row with a branch. 5 in a row with a different branch. Careful with that one, right? Numbering from this side would be the same as numbering from that side, so this is 2, a repeat, so we don't want that one. But what is different is one in the middle. That's the difference between a 2-methyl and a 3-methyl pentane, just the location of the branch. We can go down to 4. If we have 4 in the parent, we need 2 more to make our total of 6, so we can do 1 on each, but we can also do 2 on 1. 2 on 1 here would be the same as 2 on 1 there, so we don't want to repeat that one. So it turns out here, there's 1, 2, 3, 4, 5 isomers. Some students might say, how do you know when to stop? Well, if you go down to 3, you still need 3 more carbons. And once you put in 4 and 5, which is what we did over here, you'll break the octet rule if you try to draw another bond to that one. So as soon as you avoid breaking the octet rule by adding one outside of that, we're going to start to repeat ourselves, and that's not what we want. So eventually you're going to get to a point where you can't add atoms. You're either going to break the octet rule or repeat yourself. That's when you know when to stop. For introchem purposes, it's easier just to memorize for the homework that larger molecules have more. And specifically in your homework, these are the only 3 that are mentioned for the hydrocarbons. And that's going to be the ones that you'll need to know the answers for. So butane has 2, a normal pentane has 3 isomers, and a normal hexane has 5 isomers. You'll also see briefly isomers mentioned for hydrocarbons with, say, a halogen. So if you have a chlorine, you could attach the chlorine if there's only 3 carbons. You could attach the chlorine to the first one. You can attach the chlorine to the second one. So there's 2 isomers there. Just know that if you attach it to the third one, that's the same as the first one, so that's a repeat. This is also the case with almost all of the examples that you see for the functional groups coming up. When it comes to isomers, there's really 2 ways to think about it. You have groups that are on the edge versus groups that are in the middle. So let's think about that real quick, this edge versus middle concept briefly, and show you what that means with some of our groups coming up. So when I say edge versus middle, what I mean is there are groups that have oxygens specifically on edges versus in the middle. As we start looking at these groups coming up, realize that edge groups are things like alcohols, where we see this random OH. So that alcohol group is very similar to an ether group that has oxygens in the middle. So notice what's different about this group is the location of the oxygen. The oxygen is either a terminal group, meaning it's on the edge, or it's stuck in the middle. And this is why these 2 functional groups are isomers. So you'll see those briefly. And the answer for our purposes of introchem is almost always 2, because they're not going to give you a longer chain where it's more complicated. They're just trying to get you to realize that some of our groups are almost identical other than the location of those atoms. In this case, edge versus middle. You'll see that repeated twice more. You'll see it with aldehydes. These have carbonyls. Carbonyls are C double bond O's that we'll see in an upcoming video. So aldehydes are very similar but different to their ketone isomers because they're in the middle. So we're going to see these individually coming up. I just wanted to mention it in the ether or in the isomer section video just because you're going to see isomer questions on these. I'm not going to revisit them in a separate video. I'm just going to tie them together here. So notice what we have here is isomers. And again, for the purposes of the homework, the answer is always going to be 2, because what we're seeing is put the carbonyl on the edge or put the carbonyl in the middle. Same kind of thing could be said for the last pair, and that is a carboxylic acid that has a carbonyl OH. And then its isomer, which is a ester. So notice in this situation, the same exact thing happens. The answer is going to be 2 for the purposes of the homework. These are isomers because they had the same atoms, just in a different arrangement. But acids are on the edge. Esters are going to be in the middle. So in all of these situations, notice the random group is always on the side. Always on the side, always on the side. Just a different orientation of how to have either one oxygen, a double bond to oxygen, or a double bond to oxygen and a single bond to a separate oxygen. Here, though, you're going to have groups on both sides for ethers, ketones, and esters. So edge versus middle is common in organic, and that's what makes a lot of groups different, because these are going to have hydrocarbons on both sides. So these typically are going to be less polar, and that's because they're not on the edge. These guys over here are going to have those OHs, at least for 2 of the 3 examples. And because they have those OHs, those are going to be super polar. And that'll help us a lot to understand some of these ideas that we see coming up. So isomers, again, same formula, different structure. You'll see several questions about hydrocarbons. Talked about those. You'll see several questions maybe about a halogen, but again, edge versus middle can help us understand that. And then you'll see a few questions about the functional groups that are coming up in our next video. And just remember that the answer is always going to be 2, because it's really just an edge versus middle concept that Introchem is trying to teach you about those pairings of functional groups. So in our last video, or 2, we'll talk about some of those functional groups specifically.